Hello, pre-calculus students, calculus students, and any general seekers of truth. In this video, we will work through a problem here and arrive at some results that are quite significant in the history of mathematics and knowledge in general. And I'm really not overstating that. I know it sounds like I'm exaggerating, but it's really not an exaggeration at all. So let's begin with the problem here. An object was launched forward. Its position is given by the following function, where t is the number of seconds since launch, and f of t is the distance from the starting point in meters. What is the average speed between 2 seconds and 3 seconds? So let's number these questions so we can refer to them easily. And remember that for number one, average speed is nothing more than the change in position divided by the change in time. And so we can calculate the average speed in this problem relatively simply. We can say that f of 3, that's the position at 3 seconds, minus f of 2, that's the position at 2 seconds, all divided by the change in time, 3 seconds minus 2 seconds. And we'll be able to just compute this answer. Now f is 1/4 t squared, and we're plugging in 3, so this is 1/4, let's see, 3 squared minus 1/4 times 2 squared, all divided by 3 minus 2, which is just 1. And when we compute all of these mathematical terms, we get a 1.25 as our answer. And our unit here, units are important, would be meters per second. Okay, so the average speed of this object between 2 and 3 seconds is 1.25 meters per second. Now, let's move on here to number 2, which asks how fast is the object moving at, and the key word here is at, 2.7 seconds. So this question is not asking us about what is the average speed of something. It's asking what's the speed of this object at a particular moment in time. So those of you who have studied a little bit of physics, we know that this is called the instantaneous rate of change. Now in this case, this is the rate of change of the speed, so we can say the rate of change here is speed. So this is the instantaneous speed. So this object starts out at some speed and changes its speed all the time. And at some point at 2.7 seconds, we want to know what's its speed right at that moment. And this is a much more profound and difficult question because we don't really have a clear way yet to figure out. So we're going to approach this problem by a number of estimations. So let's start with estimates, right? We want to estimate the speed at 2.7 seconds. So why don't we take the average speed between 2.7 and say 2.8 seconds. So this would give us f of 2.8 minus f of 2.7, all divided by 2.8 minus 2.7. And we can plug this into the function. So this is 1/4 2.8 squared minus 1/4 2.7 squared, all divided by 0.1. And this will give us 1.375. Let me write this again. So once we do that computation, we get 1.375, which is wonderful. Now, it's not a perfect answer, but it's probably better than what we had before. So this is an estimate. I shouldn't box this in. This is an estimate between 2.7 and 2.8. Well, we should be able to get a better estimate, right? So, if we want a better estimate, we just use a smaller window. So why don't we estimate between 2.7 and 2.71 seconds? So this would be f of 2.71 minus f of 2.7, All of this divided by 2.8, whoops, not 2.8, 2.71 minus 2.7. And we can compute this math again. So we get an answer now of 1.3525. Okay, so again, a better estimate, and you can kind of see where this is going. It's kind of like anything you can do, I can do better. You can use an estimate instead of an estimate of, oh, I don't know, between 3 seconds and 2 seconds to find this answer. This is a gross approximation. We can get a better estimate by going between 2.8 and 2.7. But to get an even better estimate than that, we can go between 2.71 and 2.7. And if we want a better estimate than that, we can go 2.7000001. And we just keep adding 0001s until we get a better and better estimate. So where is this going to end? Well, before I answer that question, let us consider one thing here. Namely, graphically what's happening here, right? So it's not just algebraically, but graphically there's something important going on here. So let me get my tools in order here. All right, so let's see what's going on here. So this curve here, f of t equals 1/4 t, and now there's a left side to this as well, but we don't particularly care too much because we're dealing with positive time only. And this is t, this is time, and this horizontal direction. And let's say at this point, 2.7 and 2.8, let's say this is not drawn to scale, 2.8. Well, when we calculated this number here, what we're effectively calculating is the slope of this line. Let me explain a little bit more about what I mean. Just think about this. This is change in y over change in x. So what is change in y over change in x if it's not the slope, right? So really 1.375 is the slope of this blue line right here. Well, whoops. So what's important here, not just getting numbers, but making sort of a graphical interpretation of this. So this is 2.8. This is the slope of this blue line here is 1.375. Now we can get a little bit better, right? We can get better by calculating the slope between 2.7 and 2.71. So 2.71 is like this red, let's say it's this red dot right here, right? And then I can draw a shape. I can draw a red line, which is effectively going between those two dots right there. So I get a slightly better answer if I go between this second dot here at 2.71 and 2.7. Well, how do I get a perfect answer? How do I get an exact answer? Well, where we're going with this is we're going to end up having to take a limit. Okay, so let's say that I pick some arbitrary distance here, and we're going to call it h. Okay, so h here is the distance between 2.7 and some point to the right of it. And let me illustrate with kind of the more practical or the more concrete example. In this case right here, h is 0.1. Okay, so let's lower it down. Let's get some values here. So the exact answer, we're going to take f of 2.7 plus h minus f of 2.7 all over 2.7 plus h minus 2.7. Okay. And I realize, yes, this denominator is going to simplify, but I will simplify it later. So in this example here, h is exactly equal to 0.1. Right? So 2.8 is 0.1 bigger than 2.7. In this example here, h is equal to 0.01. And now, so now we can get like a better estimate. Right? So we want the best estimate. What we want to do is take the limit as h approaches 0. So all we're doing here is going a little bit to the right of the point where we want to make our estimate, and we're going to move that point closer and closer to where we want to make our estimate, to 2.7 in this case. So let's see what that gives. Okay, well, the first thing that I'm going to do is just simplify the denominator. So we know that 2.7 plus h minus h, that's just going to be h. And then remember, I'll write on the side here, f of t is 1/4. This is just the information that was given to us, is 1/4 t to the second power. Okay, so f of 2.7 plus h, this is 1/4 of 2.7 plus h, quantity squared, because all we're doing is we're taking 2.7 plus h, plug it into this function, minus 1/4 2.7 plus h, or 2.7 squared. All right, so let's work out all the arithmetic here. Let's see what we have. We have 1/4, and if I distribute everything, I get 2.7 squared, which is 7.29, plus 5.4h, plus h squared, minus 1/4 times 2.7 squared turns out to be 1.8825. All of this over h, and don't forget we are taking the limit as h approaches 0. Now remember, with our work with taking limits, we cannot just substitute 0 in for h. That would give us division by 0, which is problematic. But let's see what happens as we continue. Where I'm going to distribute this 1/4 here. So we're going to 1/4 times 7.29 is 1.8825. Excuse me, I need to fix this. It's not 8825, it's 8225. So 8225. Similarly here. This is 1.8225 plus 1/4 times 5.4, which is 1.35h plus 1/4 h squared. We still have this negative 1.8225 here to deal with, and all of this is over h, and this is the limit as h approaches 0. So I'm going to continue here. The tedious work is almost done. One of the wonderful things about it is that you get this number and this number that cancels out, and then we can fairly quickly factor out an h in here. So what we end up over here is h and then 1.35 plus 1/4 h, all of this over h, and we are taking the limit as h approaches 0. H on top and h on bottom cancels, and then we can finally perform direct substitution, take 0 and plug it in for h, and we get this is equal to 1.35 meters per second. 1.35 meters per second. Now this, again, I said, is a very significant number because it says that at a very specific instant in time at 2.7 seconds. Let me go back to the question. Right at 2.7 seconds, the speed of this object at that moment, and at that moment only, is 1.35 meters per second. So this is not an average speed. this is an instantaneous speed, or the instantaneous rate of change. This is an instantaneous speed. And mathematicians have tried to find a quantity like this for a very long time, but the method that they use over the years is always difficult until two guys named Newton and Leibniz came along and they developed this method of using the limit. And so this is really the birth of calculus. The birth of calculus began with what's known as a problem that deals with instantaneous rate of change. So this is your first true introduction into the wonderful world of calculus. As always, ask for help if you need it. Thank you for watching and have a wonderful